As you can see, it's my verilog generation pipeline. And what's so nice about the system is I have a front end running in React JavaScript and in back end running in Python fast API. Now I'm just going to run through an example prompt of how the system works as a 5-stage pipeline with a design input and then a mermaid architecture which renders SVG, which is great for things like state machines and just general architectural inspection. That's why I really like using mermaid diagrams for that. And I'm just going to run through a combined prompt, so the dual multimodal input. So here's a design description, design a mealy finite state machine with a detecting sequence of 101 in 0 input. And I'm going to attach the mermaid diagram that I have. And now what's going to happen is after this stage here, a user, let's say there's a user of the system here, they can view the architecture of it. And that's what I'm going to do. I'm going to go down and click the architecture. And now you can see this is the mealy finite state machine of the exact specification that was given to it. And now this is what the user would use for a multimodal input into the system. And this context is great for LLMs to actually design systems because now they have more architectural understanding of it. And now the user can also manually manually edit the mermaid code if they want to, but it's not so important now. Now click on generate verilog code, and now the system is going to make an API request to the LLM. As you can see, the API request is here. It generated verilog code. And yeah, now after that, it's going to give a few stats, total lines, modules, etc. But that's not so important. Any LLM can do that. But now it's going to run the actual simulation. And now it's going to give you a test bench that was generated in the code. It's going to run and output a VCD file. And then VCD file is now going to get parsed through and converted to a CSV file. And that's where the waveform can actually get inspected in. CSV file being output onto the screen with lines up and down to actually view the waveform, which you're going to see right now, the simulation just running. But that's what's great for actually training my deep learning model as well for my variational autoencoder, is that CSV is a lot more reliable in terms of the accuracy that a VAE can get versus image reconstruction, and a lot more accurate too. So here it is. Here's the waveform output, the console output, and the compilation output. And I think it seems about right based on my knowledge of mealy finite state machines, which is very limited, but that seems about correct to me. Just on inspection. And yeah, so that's an architectural decision I made with CSV being fed into LLMs just for more contextual understanding. And also my deep learning models train a lot better on data points as opposed to graphical input. Now, the verification results is going to show you how the LLM perceives the waveform generated and also the VAE perceives the waveform generated. So let me just click on the verification results. And now you can see the VAE, variational autoencoder, viewed it as correct. Claude viewed it as correct, or a normal waveform, and GPT-4 viewed it as an anomaly, meaning that it doesn't think it's correct. But important context is that Claude is a lot more accurate than GPT-4 in situations like this, because it has a larger context window and a better LLM architecture for things such as waveform verification, because it perceives context a lot better. So GPT-4 is prone to more hallucination from what I've seen, and also the research and testing that we've demonstrated in the report will show you the actual results of it. So that's essentially how the system works. It's a 5-stage pipeline process that automates verilog code generation and verification. Now, obviously in testing, I have scripts to manually make all these API endpoints and not just input it via a user interface. But my report is made off of automated testing. But right here you can see how everything is working. Just look at all the analysis details, you're free to read that. Now, let's just look at how the system reacts to a prompt. Whoops. Just wait for my connection to reestablish. There we go, system online. The health endpoint is responding. And let's make it the same way, but with just the prompt only, just to show that, maybe you want to do it via prompt only. Let's show you how the system works. It's exactly the same. In this case here, it'll run the code straight away. If you're doing a prompt, it won't confuse the LLM with an architectural understanding of it. There you go, code. As you can see, it's a few less lines of code with the prompt only versus and a few different statistics. Simulation is going to run the same as before. And let's see if it outputs a similar waveform or if it's actually correct. As you can see, my API, this is my backend API running. It means that it's generating verilog code just for inspection that my system is working. There we go. It looks pretty much the same as before, so I'm guessing it's going to give us very similar results. Here in this case, the prompt actually gave the correct output. Apparently, well, the metrics with VAE is slightly different because there's fewer lines of code, slightly. But overall, the 2 to 3 consensus voting appears to be that it's correct in this sense here. GPT-4 is very conservative, and like I said, in the research, Claude performs a lot better for waveform verification. But the 2 to 3 consensus voting, GPT-4 does catch a few things that the others don't as well due to the architectural differences. But the 2 to 3 voting does often not change everything.